Hello students, in this video I am going to discuss how divisibility relation can be considered as a partial order relation on the set of whole numbers. So the underlying set that we are going to consider in this video is going to be the set P, which is the set of whole numbers, which is the set 0, 1, 2, 3 and so on. And some books are in the habit of denoting the set of whole numbers as n naught, just because of the reason that the set of whole numbers is the set of natural numbers union 0, where we know that the set of natural numbers is the set 1, 2, 3 and so on. So just because whole numbers can be written as the set of natural numbers union 0, so that is why some books are denoting the set of whole numbers as n naught. Now what I do is I define a binary relation less than equal to, define a binary relation less than equal to. We are just denoting the binary relation by less than equal to. This is not the less than equal to which we understand in the usual sense, but this is just a notation. So define a binary relation less than equal to on P, which is the set of whole numbers, as the divisibility relation, because we are discussing divisibility relation over here. So I am defining my binary relation, which I am denoting in general by this sign, as the divisibility relation. So this is how the divisibility relation is defined. Now because my underlying set is the set of whole numbers, so I pick up any two whole numbers. Let's say I pick up m and n belonging to n naught. So for m and n belonging to n naught, which is the set P, the underlying set P, we say we have that m is related to n. We say that m is related to n, which is written like this: if m divides n. This is the notation that we use for saying that m divides n. And what do we mean by saying that m divides n? Saying that m divides n means that we should be able to write n as k into m for some k belonging to the underlying set. The underlying set is the set of whole numbers. So this is the definition of divisibility relation. So let me just again repeat what is the definition of divisibility relation and how are we defining divisibility relation in our case. Since our underlying set is the set of whole numbers, which is n naught, so I pick up any two whole numbers m and n belonging to n naught, and I say that m is related to n. If m divides n, this is the notation that we use. And what do we mean by saying that m divides n? Saying that m divides n simply means that I should be able to write this right hand side n, this n which I am enclosing in a box, I should be able to write this n as something into m, something into m, and that something here in this case I am calling as k, and k should come from n naught. If this happens, if I am able to write n as n is equal to k into m, then I say that m divides n. So with this definition of divisibility, we can just pick up randomly a few whole numbers and try to find out where one divides the other or not. So if I pick up 2 and 4, let's say, I know that both are whole numbers, and I can just see that 2 divides 4. Why? Because I can write this 4 which I have enclosed in a box as 2 into 2. This 2, I can write 4 as 4 is equal to 2 into 2. This something into 2, this something which I am underlining, this is playing the role of k, and this is coming from the set of whole numbers. Again, if I compare 3 and 6, I have that 3 divides 6. Why? Because this 6 which I am enclosing in a box can be written as something into this 3, something into 3, and that something is obviously 2, and this something is coming from the set of whole numbers. Then again, if I compare 1 and 0, I can see that 1 divides 0. Why? Because I can write this 0 which I have enclosed in a box, this as something into 1, and that something should come from the set of whole numbers, and this is obviously 0. So likewise, given any two whole numbers, we can find out whether one divides the other or not. If we are not able to if you are not able to write n as k into m for any k belonging to n naught, this means that m doesn't divide n. Because if m has to divide n, if m divides n, then I should be able to write n as something that something I am calling as k, that n should be written as k into m for some k belonging to n naught. This should happen, and if we are not able to do this, then we say that m does not divide n. So as I said, given a pairs of whole numbers, we can always find out whether one whole number divides the other or not. Now once we are clear with the definition of divisibility, my aim in this video was just to show that divisibility relation is a partial order relation on the set of whole numbers. So in order to show that divisibility relation is a partial order relation, we already know what a partial order relation is, because I have already made a video on partial order relation, and there I have already defined that a relation, just for the sake of recalling, in this particular video, we say that a relation less than equal to on the underlying set P is said to be a partial order relation if it satisfies three properties: reflexivity, antisymmetry, and transitivity. When do you say reflexivity is satisfied, or when do you say that a relation less than equal to is reflexive? A relation less than equal to is reflexive on the set P if for every element m belonging to P, m should be related to itself. If m is related to itself, if m is related to m, then you say that the relation less than equal to is reflexive. Then when do you say a relation less than equal to on P is antisymmetric? The relation less than equal to P on P is less than equal to on P is said to be antisymmetric if for any pair of elements m and n that you choose from P such that m is related to n and n is related to m, if this collectively implies that m is equal to n, then you say that antisymmetry is satisfied. Then the third and the last property is the transitivity property. When do you say that a relation less than equal to is transitive on P? If you pick up any three elements m, n and P belonging to P such that m is related to n and n is related to P, then this should collectively imply that m is related to P. That is, if the first element is related to the second element, and if the second element is related to the third element, then this should collectively imply that the first element should be related to the third element. Now if these three properties are satisfied, reflexivity, antisymmetry, and transitivity, if these three properties are satisfied, then you say that the relation less than equal to on P is a partial order relation. We have already done this in my earlier video. If one is interested in knowing more about what a partial order relation is, and one wants to learn more about examples related to partial order relations, one can always refer to those videos. Now coming to what we had to discuss in this particular video. In this particular video we had to show that the divisibility relation less than equal to, which we have denoted like this is a partial order relation. Now in order to show that it is a partial order relation, we have to show three properties: reflexivity, antisymmetry, and transitivity. So the first thing that I show is that less than equal to, or the divisibility relation, this is reflexive. So let me take any m belonging to the set of whole numbers. So for m belonging to n naught, we have that m, we can see that m is related to m. Why? Because m divides m. And why does this happen? Because we can write m divides n as m divides m. Why? Because we can write this m, which I have enclosed in a box, this m as something into this m, something into this m, and that is 1. M can be written as 1 into m. So because we can write m as 1 into m, where this 1 belongs to the set of whole numbers, so that is why m divides m, or m is related to m. So because we had chosen m to be any arbitrary whole number, so that is why this property holds for all the whole numbers, because m was chosen arbitrarily. So this relation less than equal to, or divisibility relation, is a reflexive relation. Coming to the second property, that less than equal to is antisymmetric, which is the this relation, this or the divisibility relation, this is antisymmetric. This is what we have to show. So let me pick up two numbers m and n belonging to the underlying set, which is n naught. So let m belonging to n naught and n belonging to n naught be such that m is related to n and n is related to m. We just have to show that m is equal to n in order to show that less than equal to is antisymmetric. Now because m is related to n and n is related to m, so this implies that m divides n and n divides m. and this means that I should be able to write this particular n which I am enclosing in a box as something into m, and that something into m is k1 into m, let's say, where k1 is coming from the set of the underlying set, which is the set of whole numbers, and I should be able to write this particular m which I am enclosing in a box as something into n, which means let's say k2 into n, where this k2 is coming from the set of the whole numbers, where whole numbers is the underlying set. So k1 and k2 belong to n naught, which is the underlying set. So now these are the two expressions that you have, n is equal to k1m and m is equal to k2m, and consider any of the two. So let me take n is equal to k1m, consider this one. Now in this expression put the value of m from here, so this is equal to k1 into k2n, I am putting the value of m. Now this can be written as k1 k2 into n. I am changing the order of the brackets because everything is coming from the set of whole numbers, and associativity holds in the set of whole numbers. So you can change the order of the brackets. So you can either write k1 into k2n, or you can write k1 k2 into n, and so this is what we have. So this finally implies that I have been able to write n as k1 k2 into n. And now this particular expression can hold, the left hand side can be equal to the right hand side only if k1 k2 is equal to 1. So the product k1 k2 should be equal to 1, where we know that k1 and k2 both are coming from n naught, the set of whole numbers, where the set of whole numbers is this 0 1 2 3 and so on. And since the product of k1 and k2 is 1 and both of them are whole numbers, there is no other possibility other than this one, that k1 and k2 both of them have to be equal to 1, because only then their product can be equal to 1, as both of them have to be whole numbers and their product has to be 1. So there is no other possibility, both of them have to be equal to 1. Now using this fact, this particular fact, that k1 is equal to k2 is equal to 1 in any of these two expressions. So let's say I pick up this one, this particular expression, n is equal to k1m. So using k1 is equal to 1 in n is equal to k1m, we get, putting the value of k1, we get n is equal to m, and this is what we had to show for antisymmetry. So we started with m is related to n and n is related to m, and we have got n is equal to m, which shows that this relation less than equal to, or the divisibility relation, this is an antisymmetric relation, because m and n were chosen arbitrarily and they were satisfying these two properties, but they were any arbitrary whole numbers which are satisfying these two properties, which means that any two whole numbers which satisfy this property, that m is related to n and n is related to m, this would always imply n is equal to m. This means antisymmetry holds. So the second property also holds. Now coming to the third property, the third property is transitivity. Now let me find out whether this relation less than equal to is, or which is the divisibility relation, this is transitive or not. Now in order to check transitivity in the set of whole numbers with respect to the divisibility relation, so let me pick up m, n and p to be any three whole numbers such that m is related to n and n is related to p. Now what is that you have to show? You have to show, in order to show that less than equal to is transitive, we just need to show that m is less than equal to p. So we actually have to show that if first element is related to the second and second element is related to the third, then first element should be related to the third. First element should be related to the third. This is what we have to show. So we are supposing that m is related to n. Because we are supposing m is related to n in our notation, this means that m divides n, because divisibility is the relation that we are considering. Again, we are also supposing that n is related to p, which in our notation means n divides p. So because m divides n, this means that I should be able to write this particular n, which I am enclosing in a box, as something into m. So this particular m which is on the right, I should be able to write something into m, and that something I am calling as, let's say, k1, for some k1 belonging to the underlying set, and the underlying set is your n naught, which is the set of whole numbers. Again, also I have that n divides p, which means that I should be able to write this particular p on the right as something into n. So I should be able to write this p which I have enclosed in a box as let's say some k2 into n for some k2 belonging to the underlying set which is n naught. So these are the two expressions that you have. Now what I do is I consider the second expression, which is this one. So consider p is equal to k2n, and in p is equal to k2n I put the value of n. The value of n is here. So this is equal to k2 into k1m. I am putting the value of this particular n from here. And now by associativity, because everything is happening in the set of whole numbers, and in the set of whole numbers associativity holds, so you can put the brackets in this order. I can change the order of the brackets. So k2 into k1m can be written as k2 k1 into m, and now this particular k2 into k1, this particular product can be written as k, just for simplicity, because I don't want to write this again and again. So this product k2 k1 can be written as k into m. So therefore what do you have? You have that p is equal to k into m, where this k was k2 into k1, and since k1 and k2 both were coming from the set of whole numbers, so this whole thing, the product also belongs to the set of whole numbers, because product of two whole numbers is a whole number, so k is also a whole number. This means that I have been able to write p as something into m, which means that I can say that m divides p. Why? Because I have been able to write this p, which I am enclosing in a box here, as something into m, as something into this m. So m divides p. This one can be written as m is related to p, and this is what we had to show, because we started with m is related to n and n is related to p, and we had to show that m is related to p, and we are over here that m is related to p. So this means that transitivity holds in the set of whole numbers with respect to the divisibility relation, because if we are picking any three whole numbers m, n and p which are behaving like this, that the first is related to the second and the second is related to the third, then the first becomes related to the third, which is this happens. So this is happening for any three whole numbers which are behaving like this. So transitivity holds. So this means that all the three properties, reflexivity and antisymmetry and transitivity, all the three properties hold in the underlying set, which is the set of whole numbers, with respect to the relation less than equal to, which is the divisibility relation. Therefore the divisibility relation is a partial order relation on the set of whole numbers. Therefore divisibility relation, this is a partial order relation, or we can say divisibility relation is a PO relation on the set of whole numbers, which is n naught, which we have denoted as n naught. So this is what I had to show in this particular video.